one of the beauties of this thing is that you can start from very elementary things, and that's what I'm going to do right now. And then we can move on to more involved, more complicated stuff. But we shall see. So what I'm starting with is actually a nice high school math problem. So you may know this problem, but even if you know this problem, probably you don't know this particular solution, this particular approach to the problem. Here's the problem. So you have a half line, and you have 2 point particles on that half line. This has mass m2, and the one closer to the end of the half line is of mass m1. And actually, m2 is bigger than m1. Okay, these are just point masses. And you give this mass a little kick, this ball. You give it a little kick. So what happens is that it's going to, this is absolutely frictionless ideal motion on the half line. It's going to move uniformly until it reaches the first one. Then it collides. Then the bigger one turns back, and the lighter one picks up a speed which is bigger than the speed of the bigger one, and then it bounces back. Okay, and then it catches up, right? Catches up with the other one. It chases, and it bounces back and back and back. And what's going to happen eventually that the light one speeds up the heavier one. So eventually, what's going to happen that both of them go off to infinity, right? Yeah? Because eventually the smaller one will have smaller velocity than the lighter one. It catches up to some time. Okay, so this is the question. How many times do they collide before this happens? Okay? Is the question clear? Yeah? So how many collisions are there? Before, so let's say v2, that's the velocity of the lighter, of the heavier particle, is greater than v1. And of course, as soon as this happens, there are no more collisions, because then the lighter one can no longer catch up with the smaller one. Okay. So, of course, this depends on the mass ratio of the particles. So, how can you find a solution to this problem? Well, and then just let's denote by x1 and x2 the position of the particles. Then apparently there are constraints. If this is my origin, then x1 is necessarily greater than 0 because it's right to the origin. And x2 is greater than x1. Okay? So this means that if I would like to specify the state of my system, this is x1 and this is x2, then this is the diagonal, and actually things are happening in this wedge, right? Okay, that's where things are happening. And just like I already indicated here, I introduce the velocities for these particles, which are just, okay, these are signed quantities. They correspond to the derivatives of the positions, right? Okay. So apparently, if I have just a point here, this means that the particles are located somewhere. They have a certain velocity. Then this means that they proceed along a straight line. Okay. When they reach this particular line, which means that x1 is 0, then the light particle is reflected from the back. Okay? So this just turns back, right? And then when they reach this line, yeah, then something else is happening. And what else is happening can be determined by the following equations. There's conservation of energy. Which means that m1 v1 squared plus m2 v2 squared is constant. It takes the same value before the collision and after the collision. You may recall this from your high school physics studies, how that was. And the other is conservation of momentum, which says that m1 v1 plus m2 v2, this is a quantity that already has some sign. Yeah? Okay? This is again constant. Okay. This happens at both collisions. These relations happen to be true at both collisions. Okay. So these are the things that determine the before velocity, that connect the state of the system before collision and after collision. Okay. So here comes how it relates to billiards. So let's introduce, instead of the original x1 and x2, yeah?
Sorry, when x1 is 0, then the impulse sign is...
Yeah, but, yeah, okay. This corresponds to collision. So this corresponds to bi-particle collisions. Okay, this is not true when the one collides with the wall. This true. Yeah, your remark is absolutely in place. Okay, thanks. So, okay, so here what here's a way to approach this problem. Instead of the original xi, I introduce new variables, which are rescaled by the square root of the masses. Okay. So then the original relation changes. x1 is still greater or equal to 0. x1 prime is still greater, x1 bar is still greater or equal to 0. But the relation here becomes like this. Yeah? I guess so. Yeah? That, how is that? Or, no, the other way around, right? So, because if I denote by x2 bar the position of the second particle, I got to divide by this quantity to arrive at the position of the other particle. Okay? So you have a relation like that. So what happens that in these coordinates, x1 bar and x2 bar, this is no longer such a wedge. This wedge is like this, where the motion of the particles takes place. Yeah? It's a smaller wedge. Okay? And this wedge has an angle alpha, right? Such that the tangent of alpha is equal to square root of m1 over m2. Yeah? So the more uneven the masses are, the smaller the wedge is. Yeah? Okay. So what happens to these relations, 1 and 2, upon this change of momenta? What happens here is that vi bar is, of course, square root of mi vi. Yeah? So v1 bar squared and v2 bar squared just equal to constant. Okay? That's what I have. So in these coordinates, the length of this vector, of the velocity vector, is constant. Okay? On the other hand, what happens to these relations is that square root of m1 v1 bar plus square root of m2 v2 bar is equal to constant. Okay? And just realize that this vector, square root of m1, square root of m2, is parallel to that line. Yeah? So this is parallel to that line. So this relation says that the momentum of conversation means that the component upon collision with that line is preserved. Yeah? This means exactly that it is a reflection on that line. So let me just turn this picture upside down. Okay, here I have this wedge alpha. Yeah? So what I have here is that I start my point like this. Then if I reach that line, I have a specular reflection. Angle of incidence equals angle of reflection, and so on and so forth. I have again reflection, 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 and eventually I turn back. And then what the question is, how many times do I collide altogether in the course of this process? Okay, so this is a billiard in this wedge of size alpha, and I'm asking you, how many times do I collide in this wedge before I leave? Okay, and here's an answer to this question. When you reach the boundary of your table, don't reflect the billiard trajectory. Do reflect the table. Okay? This is the same. Okay? And so on and so forth. And proceed along these lines. Question is, how many times you reflect before you go off? Yeah? And the answer is, of course, so the number of, well, this is the number of collisions and reflections altogether. So you divide by 2 to get the number of collisions. So it's pi over alpha. Well, ceiling on that, because actually you have another one. Yeah? Before leaving, before going off. Okay. So this is pi over the arctan of the square root of the masses. M1 over M2. Yeah? So that's the answer to the question. In fact, if this M1 is just a piece of dust of 1 micrograms, and this M2 is a large rock of size whatever tons, then the number is going to be, how much is going to be? It's going to be the first couple of digits of pi. Yeah. So it's a machine that measures pi, in a sense. Yeah? Of course, you need to tune this very, very, very precisely to arrive at such a conclusion. Okay, so I think this is a...
What do you mean measures pi? For like 3.4 pi.
Yeah, sure. No, it measures an integer number of times, but if this is 10 to the k, then it's going to be k half or something. Yeah, that's what I meant. So if you could tune the mass ratio very, very nicely, you could get an approximation of the first couple of digits of pi. Okay, so actually, this is just, I think it's a nice little problem for high school camps or something, but it has two interesting messages, I think, which are relevant for billiard. The one of the messages that you can represent several particles as a single point in a higher dimensional domain. That's what we did. So instead of considering the individual particles, we took just one point and considered the motion of that one. And the other interesting feature of that is the unfolding procedure. I call this the unfolding procedure of, instead of reflecting the particle, reflecting the domain. Okay. So these two features are kind of characteristic and would crop up at other instances of billiard. So okay, let's have a look at some other billiards, and let's try to first put our hands on the tools that are relevant for studying these objects. Okay, so the second one that I'm going to consider is still quite elementary. This is a billiard in a circle. Okay. So here it's quite easy to understand what's happening. So I'm considering the motion of a point particle inside a circular domain, and when it reaches the boundary, it reflects off elastically. And what I see here is that, okay, here I have a certain angle that I make with the normal of the table. And what I observe is that at the next collision, I'm going to take the other point with the same angle. Okay, so this is actually a constant quantity. So this suggests the following description of the dynamics. Let's introduce a phase space which is just consists of pairs r and phi. So R is location of collision measured in arc lengths from a specific point along the boundary. Okay, this is one coordinate. And phi is angle of outgoing velocity and normal vector. So phi is from the interval minus pi over 2 pi over 2, yeah? I can have these two extreme values for the collision angle. While this coordinate is cyclic, right? Because if I go around, I will get back to the same position. So I identify the first and the last value of the coordinates. So actually, this phase space is a cylinder. Yeah? I have a cylinder. So I represent this cylinder, of course, as a rectangle. This is the phi coordinate, and this is the r coordinate. This is minus pi over 2. This is plus pi over 2. And how does the motion, in case of the billiard in a circle, for a circle, how does the motion in this phase space look like? I'm asking you if the position is some r and phi in M, what is r1 phi 1 that I'm going to denote by t of r phi at next collision going to be? Okay, so if I'm here at a specific r and phi, this is r and phi, what is r1 and phi 1? So what I would like to understand is a map which maps M to itself. Tells you where I am, then what is going to be my next position on this phase space. And it's not hard to understand that actually these curves, specifically for the case of the billiard in a circle, these are invariant. So once I'm on such a curve, I will stay on such a curve for all times. If this is my r phi, this is going to be my t r phi, this is going to be my t2 r phi, and so on and so forth. Okay? So what I have is that these curves are invariant. So invariant curves. Okay? And on these invariant curves, what I have, these are actually, observe that these are just loops around M. Yeah? The starting point and the ending point of this curve is the same because it's a cylinder. Yeah? And what I'm doing is that I'm hopping with a constant speed along these curves. And how much I'm hopping depends on the value of phi. Okay? Here I hop a little more. Yeah? Because what I hop is a function of phi. And the closer I am to the diameter, the longer I hop. Okay, so this is what I'm having here. Okay. Actually, these are, in ergodic theory, these objects are one of the first examples. These are the rotations of the circle. So you have a rotation of the circle along each of these invariant curves. So this is something that's pretty well understood. We call this an integrable motion. Actually, just an analogy that if you consider the solar system and you consider the motion of the planets around the sun, you have exactly this type of motion. Depending on your distance from the sun, you observe such a periodic motion. Okay. And it's a very interesting question, what happens when you try to perturb such a thing? When you add some additional effects. Do these invariant curves remain? Or are they destroyed by the perturbation? This is something that has some practical significance also for planetary motion. Okay, so now take a variant of this thing, and you will see that this thing is just destroyed. Okay, so what I'm doing now is that I cut this circle in two halves. Okay, and I remove the two halves a bit from each other. It's enough to move them an epsilon distance away. So take two semicircles, move them a little bit apart, and connect them by straight lines. Okay, it's clear what has happened. Okay, this is a famous billiard. This is called the stadium billiard. And I could ask the same thing. I could introduce the same coordinates, r and phi, like before. I have the same phase space structure, r, phi, and I'm asking you, what does this map do in such a case? Okay, there are points which behave very similarly like before. For instance, this one. This corresponds to a particular value of r, and phi equals 0 because it's a perpendicular motion. And of course, this just goes here to some other point, and this one goes back. So it's a similar kind of rotation, as it seems. But if I just pick one point at random, say this one, what I'm going to see is something like this. It's going to be all over the place. So, well, there are some other periodic guys, but these form a discrete set. These form a countable collection of points. So what I typically see is such a thing. Well, actually, there are some interesting one-dimensional families of periodic points here, like those bouncing back and forth. They play an important role in the dynamics of the stadium billiard. So we see this. And here I would like to address two questions. First question is how to describe this. Apparently, here I could give a very explicit description of what's happening. But here, it turns out that studying the individual points, individual trajectories, is not very fortunate. It doesn't lead to anywhere. So this is the first question I would like to ask. And the second question I'd like to address is, why is that so? Why do I see such an unpredictable motion, an unpredictable pattern on my phase space? So these are the questions that I like to address.
So for a typical starting point, the trajectory will be dense here?
Yeah. For a typical starting point, the trajectory will be dense. Actually, it's going to equidistribute in a sense. Okay. I'm going to tell you in a minute what I mean by this equidistribution. So it's more than dense. It's going to be dense in a uniform way. So actually, for a typical phi, it's going to be dense on the curve, even here, just because if phi is irrational, these points are going to fill the invariant curve densely. But this restricts to the curve. Yeah? So, before going further in the answer of this question, let me give another example. So here, at first sight, my billiard domain is going to be infinite. So just take the square lattice, Z2, and into each lattice site, put a little circle. Yeah? That's what you're doing. It's clear, okay, what I'm doing. In each lattice site, I put a circle of a fixed radius, like radius 1/10 or something. And then again, I can take the complement of these circles on the plane. So I take R2 minus circles. And here I can play my billiard. So what I do is that I pick a point, extend it with a velocity, and let it go. And then, well, I don't know. You see what's happening. It's traveling all around. So this is already a model which is of some physics interest. Why? You can think of this particle as an electron, and you can think of these fixed balls as if they were atoms in an insulator or in a conductor, and you're asking, what is the conductivity of that material? That is, what does this little particle do? Okay, so this is a very famous model, which we call the Lorentz case. Lorentz gas. Okay. So what's not so convenient about this description at first sight is that you need to treat an infinite object. And it's no matter what you do, you know that bounded compact objects are nicer to handle than infinite objects. But because of the periodicity, we have a periodicity, you can reduce this to a compact object. Namely, what you do is that instead of an infinite periodic configuration on Z2, you just, this time you don't unfold, this time you fold, right? So this time you fold, when this leaves, oh, I say, actually this one enters here, and then this one enters back here. So what I do, that by folding, I reduce this thing to a billiard in the two-dimensional torus, T2, yeah? Okay, which is just R2 factorized by Z2, okay, by this folding procedure. So what I get, this is no boundary, this is just an indication that these two sides and these two sides are identified, okay? What I have here is this type of motion, and here I observe a reflection, and so on and so forth. Okay. And here I can play the same game. I can introduce the same type of M. Yeah? Along my scatterer, I introduce the coordinates R and the collision angle. This time, it's at the exterior of the scatterer. So when the trajectory comes in, here I take my phi, which is my angle of outgoing velocity with respect to the normal of the scatterer. Okay, and as before, I have S1 cross minus pi over 2, pi over 2. And actually, this turns out to be even more chaotic in a sense than the other. So here, what I see is the same type of phenomena. In a some sense, it's even more apparent than in the other case. Okay, let me just make one more remark about this Lorentz gas. The one that I drew on the board is a so-called infinite horizon Lorentz gas. What do I mean by this? I simply mean that the length of the free flight between two consecutive collisions is unbounded. Okay, I can fly indefinitely long. For instance, if I here go off almost horizontally, then I can fly an infinitely long, an unboundedly long time before colliding at the next collision. So, and why I'm saying is that there are actually finite horizon Lorentz gases. No. It's not linear. This thing is going to converge to Brownian motion. Well, I should be a little more precise. You are running ahead, but no problem. Since you asked, let me tell this. So just one remark that instead, how you create a finite horizon Lorentz case, this is related. This is related to your question, so that's why I'm mentioning this, that instead of a single type of scatters placed periodically, now I have two types of scatterers. Yeah? This is scatterer A, this is scatterer B, B, B. Observe that these four scatterers are actually the same scatterer on the torus. Yeah? You see what I mean? So, and then this way, with two scatterers, actually, I can create a configuration which is of finite horizon this time. Okay, so the answer to your question is that take an X, which is a starting point in your billiard. Actually, you could take an R and phi in your billiard and consider the position of your walker on the plane dt. So this is a position in R2. So instead of folding, now you unfold. We'll create this notion clearly in a moment. So in the finite horizon case, this scales a square root of t. And in the infinite horizon case, it goes a little faster. There's an additional log. It's not a surprise that it goes a little faster, actually. That's because you have these long flights. So the difference is that here, when you zoom out, what you see is a Brownian motion, like that. And what you see here is a Brownian motion with occasionally some long flights. And they're going to gain a long flight, and again a long flight. But if you rescale by t log t, those long flights do vanish. You do not see them in that limit. So actually, still the convergence to Brownian motion is there after this scaling. So in probabilistic terms, you're in the non-standard domain of attraction of the normal lobe because of the flight. So that's what you see. But actually, to attack this question, we can still use the compact billiard, the one with this M, yeah, with this particular M. Well, okay, in the finite horizon case, the only difference is that this time you have two cylinders, one corresponding to one scatterer and the other corresponding to the other scatterer. But otherwise, it's the same type of phase space. Yeah? Instead of one cylinder, you have two cylinders. And may happen that from that cylinder you go to this cylinder, you may go from this cylinder to the same type of cylinder, and so on and so forth. Okay, but how to decode? How to decode the position on my plane in terms of this finite object, in terms of this compact object? Well, here's how I decode it. Let me introduce a function, delta. This is just length. This is just the vector to the, well, this depends on r and phi, to the point of the next collision. On R2, on the plane. Okay, this is a function. Yeah? Which is defined, delta is defined on M, but maps to R2 this time. Okay, I have such a function. It tells me if I'm here, for instance, if I heave and with that velocity vector, then this is the value of my function. Yeah? Okay. Then I take the following object, which is the so-called ergodic sum. So the ergodic sum, for simplicity, I just denote with x, r, and phi. Okay. So I just take x, delta at x, delta at t of x, plus delta at t squared of x, plus etc. So recall that T maps M to M. It tells me where I am on the compact phase space, but I nonetheless can sum up where am I on the plane. Yeah, this will tell me my position after M positions on the plane. Despite of studying only a compact object and the function defined on the compact object. So this is my position after n times. In ergodic theory, these sums are very important. These are the so-called ergodic sums. Okay. So these are the subject of our interest. What happens to such ergodic sums? Okay. And as I said, because of this very unpredictable pattern, it's not so convenient to study the points, how they evolve on my phase space. Instead, the idea is to study measures. So no individual points, but measures instead. Yeah? How they evolve. What they tell you about the dynamics on my phase space. And this will shed some light on what happens to individual points. Okay, in particular, invariant measures are very important. Okay, what do I mean by invariant measure? It means that if I have a subset which is measurable, of course, measurability is quite clear what it means in this context. We just have a nice piece of R2. Okay? Then the measure of A must be the same as the measure of the preimage. This is what I mean by mu being invariant. That's what I mean. So in these systems, actually, there are many invariant measures. For instance, take the stadium. If I just take the measure that sits on that point and that point, the delta measures, and I take their average, I get a measure which is invariant, yeah, because the point is periodic. But what are really interesting are invariant measures which are absolutely continuous with respect to Lebesgue measure, because they are those that see what really happens on the phase space. Those that see non-periodic points, they don't see much of the phase space. They just see something very, very particular. So in fact, in these billiards, there's a unique invariant measure well, in case of the circle, it's not unique, but in the other examples, it's unique. And I can tell you what this measure is. It's essentially Lebesgue measure, but you need an additional factor cos phi to have it invariant. And, well, let me put here a normalizing constant so that it makes this a probability measure. Okay, so that the measure of the full phase space is nice. And this is good because this way I can play probability theory on my dynamical system, which is very useful. So C is just a normalizing constant so that the measure of the phase space is 1. Okay. Okay, so why this factor cos phi? I can tell you, and this relates to the mechanism that makes these things a little chaotic. The factor cos phi is there because, say you have some set of points starting off from a certain scatterer, which arrive in a very skewed way to the next scatterer, yeah? Then you see that the length of this curve is magnified just because of this projection. So in order to make the measure invariant, you need this factor cos phi. Yeah, this is exactly the scaling factor that happens after because of the projections. Okay, so this is what makes this factor cosine of phi appearing. Okay, so now I'm at the point where and how to describe these phenomena. So the first important fact about these billiards for stadium and Lorentz gas, the invariant measure mu is ergodic. Okay. So what do I mean by this? I do not suppose that you know what it means, but I tell you in a minute one possible definition of the several equivalent definitions of ergodicity in this case. This means that given a function on my phase space, and you may think about the delta over there, right? It's just as right to think about that. Take this average Sn of x, which is f of x plus f at t of x plus f at tn minus 1x. Okay. And then, instead of Sn, just divide it by n. So what do? I take an orbit, and I measure the values of my function along this orbit. And I take the average of the values that I see. And ergodicity means that this thing converges to the integral of the function. Okay? You see, no matter what x is, I'm cheating a little bit. It matters what x is, but this happens for almost every x in M. Okay? So what does that mean? Just think about it for a while. So, interpretation of this is a random variable. Why? Well, this is a function on a probability space that's integrable, right? This is a random variable. And then I can take f composed with t. This is another random variable. And f composed with t and minus 1. These are all random variables. And they are identically distributed Why? Because the measure is invariant. So you see the same distribution of these random variables because the measure of it is invariant. Okay. So you have a sequence of random variables, identically distributed. You sum them and you divide by the number of terms. And you observe convergence. What is this? Convergence to a fixed number, irrespective of what you started with for almost sure starting points. This is a law of large numbers, right? So what you see is a law of large numbers for identically distributed variables. So it's a law of large numbers, yeah, for identically distributed variables, but they are far from being independent. Those are strongly dependent random variables, right? So what you see is that despite of the dependence, which is, the dependence is what? The dependence is the billiard dynamics that kind of projects down to these random variables. Despite of that, you see the law of large numbers appearing. This is what ergodicity is, in a sense, okay? And this is the answer to your question. It's not only that for almost all trajectories are dense, they kind of give an equidistribution to the values in that sense. Okay. So that's what I observe. Okay, so how do I proceed? My next question was, why is that so? So why do I observe in this case such kind of essentially random behavior on the phase space? And I would like to first demonstrate this in the case of the Lorentz case. So what is behind this? Okay, and here's what what causes this. Actually, I already have the picture on my board. So here I have my scatterers, and if I just take a small curve corresponding to some little curve on my phase space, and I let it go, let it fly with my billiard dynamics, then this curve will actually turn into a convex curve, right, because of the scattering. And then it will grow and grow and grow because these trajectories do diverge. Okay? That's why information on my initial position is, in a sense, very quickly lost because I have this growing and growing effect. This is what I call Hyperbola City. In fact, at this point, you may be a little suspicious of what I've said. Because if I see this kind of growing, how come that something which is essentially Lebesgue measure is invariant? Okay, how is that possible? Well, the reason is that this map, T, actually has two specific directions in each point. A direction which is growing and another direction which is contracting. Yeah? So this way, this map, as it maps x to t of x, here in these directions I see a growing, and in the other directions I see a contracting. So for instance, a square like this moves into a rectangle like this. So this could be essentially measure preserving, despite of seeing growing in many of the directions. Because just think about it, anything that's transversal to the contracting direction will eventually grow, right? Because there the expanding effect is the strong one. This is what I call hyperbolicity in this case. Okay. So this is the effect that I see. But there's something more to that. Now let's get back to my phase space, and let's consider the evolution of my curve, okay, which was originally a little curve like this. Yeah? Okay? And then I let it evolve, and it grows into a longer curve, and I let it evolve, and it grows into an even longer curve, and so on and so forth. This is not yet the full story. I should tell you another important phenomenon which makes billiards a little more peculiar than other systems which have hyperbolic behavior. And this is the fact that the billiard map is not smooth, it's not continuous. So this is one of the main features of billiards, and the other main feature is singularities. So here's one of my scatters, here's another scatter, and here's a third one in between. And here's a particular trajectory. So this one, yeah, this trajectory touches my scatter. Do you see that this billiard map is discontinuous near this trajectory? That's because if I go a little down, I will arrive at this point. But if I go up, I'll arrive at this other point. Okay, so T is not continuous. Actually, it maps to two different components of the phase space. Okay, and this discontinuity would be present even if I studied things in continuous time. Not in the form of a discontinuity, but in a lack of smoothness, actually. So, spots where T is discontinuous. Actually, these spots turn out to be, in this case, a finite union of curves. These are pre-images of the boundary of the phase space. This happens exactly at the boundary of the phase space, where my angle is pi or pi over 2 or minus pi over 2. Okay, so what actually happens to these curves, so revisit the evolution of curves gamma in M, what I see is that one curve actually is mapped into a collection of curves. Yeah, they land on different parts of the phase space because of the discontinuity, and at the same time, they are getting longer. So this is a fine geometric effect, the competition of these two phenomena, growing and fragmentation. Okay, so competitive phenomena growth and fragmentation of these curves. Okay. And here's another property that that's not the one I used. Yeah. Okay. That's a very important and very strong property that appears in these billiards, and this is true for the Lorentz gaze. We have an exponential converges to equilibrium. What do I mean by this? I mean the following, that take a small curve and put Lebesgue measure on it. So 1D Lebesgue. So you have a small curve, and you put Lebesgue measure on top of this curve. And evolve this measure. You get a measure. This is a measure. So what is this measure? It means that for functions that are 0 along my curve, the integral is 0. For those functions which are non-zero along my curve, this gives something, right? Okay. And here, I can push this measure forward with my map, okay? And this measure converges to the invariant measure, okay? This is what I see. Picturesquely, that's what it means. You pick your small curve, you evolve it, it fragments and gets longer. Then you evolve the further pieces further. They fragment and get longer. And what they see, that these curves equidistribute on the phase space, faster and faster. And actually, this happens at an exponential rate. What I mean by this is that if I take a function which has some smoothness properties on the phase space, and I integrate it with respect to this measure, what does that mean? I take f t n x d lambda x. This approaches the measure, the equilibrium measure as time progresses. This means that these little curves equidistribute on the phase space. And this is very nice, this exponential convergence. Once you have this, you can deduce essentially all the properties that you would require. For instance, ergodicity, but also actually those problems like the central limit theorem. Okay, so now that we are there, I can quickly mention that actually there are strengthenings of the ergodic theorem. But first, let me tell you something else. You may be again suspicious. I told you that the stadium is also ergodic. It behaves similarly to the Lorentz case. But what I said was that we have this scattering effect, and that's behind ergodicity. So you may ask, how come? I don't see any scattering effect here. In fact, what I see, that if I start with a parallel beam of trajectories, they actually get focused, right? This is a focusing mirror, okay? But they tend to defocus. Yeah? Okay. And that's because I separated those semicircles far from each other. Okay. So here in the stadium, we have defocusing phenomena. Yeah? Which actually plays the role of the scattering phenomena of the Lorentz case. Okay. So I think, so how long should I go? Not much longer. So another 5 minutes? Would it, well, what's the usual pattern?
Usual pattern is 1 minus epsilon.
Minus epsilon, okay.
Plus epsilon is also fine.
Okay.
Yeah, 5 minutes is perfect.
One or minus epsilon.
I think 1 minus epsilon.
Okay. So okay, then maybe just one thing back to the question that we encountered a little earlier is that we observed that this is ergodicity. So this is known for the Lorentz gaze from the 70s, and actually this is Sinai. He was the one who found this. For the stadium, this is known from the 80s or something, and this is Bunyamovich. And then my next question, which we already discussed, was the central limit theorem. So what is the central limit theorem? It says that, okay, here I did a little too much, yeah? Too much little of scaling. And like in probability theory, I need another scaling, a square root of a scaling. And this converges in distribution. If x is chosen according to the invariant measure mu, x is chosen according to mu, this converges in distribution to the Gaussian law. Well, it's yet an interesting question what this asymptotic variance is. Okay, it's determined by some time correlations in the system. Okay, this is true in the finite horizon Lorentz case. And this was done by Sinai and Bunyamovich, actually, and I think something in the 80s. Okay. So now, this is what you need here, this additional log n, okay, to obtain a similar type of convergence in the stadium. And in the infinite horizon Lorentz case too, but there the effect is a little, it's essentially similar effect, but here the function is bounded, there the function is unbounded, okay? So in the stadium, and this is actually, so it's Sinai and Bunyamovich, and this is another B, this is me actually, and my friend and co-author Guezel, Sebastian Guezel. And we proved this in 06, I think. This kind of convergence. Okay. So you have here again a non-standard limit law. Yeah? And let me tell you what's behind this. Again, instead of folding, unfolding this time. Okay. So here you have the stadium. And I already told you that there are these special guys who bounce back and forth between the parallel sides. So what do you do here? Instead of reflecting the domain, reflecting the trajectory, you reflect the domain. And reflect again the domain and again the domain. So you have these long flights, right? It's like an infinite horizon Lorentz gaze, yeah? When you unfold. What you need to understand is that instead of considering the original map with these functions f on them, you create a reduced map which corresponds to returning to the circular part, and you induce the functions. And you obtain some unbounded functions which are in the non-standard domain of attraction of the stable law, of the central, of the normal law. And then you obtain this type of limit phenomena. And that's why you have this square root of n log n scaling here. There's also a difference that this is something quite complicated that depends on the dynamics, while this one is not so complicated. It can be actually calculated in terms of the values of the function along these lines. Yeah? This is the only spot where this square root of n log n effect shoots in. Okay? And in the case of the infinite horizon Lorentz gaze, so infinite horizon Lorentz gaze, we have the same type of behavior. Well, it's important that this time I take the position of the particle on the plane, because if the function is unbounded, it would converge with a square root normalization. But it is an unbounded function. This converges to something Gaussian. And this was done by Domokos Szász and Tamás Varjú. And I think it's 0.7. So roughly the same time these results were incorporated. So just very much in a nutshell, what else I would have talked about if I had more time. I would have talked about the multidimensional case. So what happens if you put, instead of circles on the plane, you put spheres in space, yeah, periodically? What happens? This appears to be a much more delicate question. Even the construction of right configurations is an issue. Here we used actually a result of Böröczky and Tardos. That such configurations where the horizon is finite actually exist. It's not clear. Which works? It's from the younger one. The young one with Tardos, yeah. The older one, did he work with Tardos? I don't know. So that's one thing. Another thing which is quite interesting is that I mentioned you this correspondence of several particles in a domain with one particle in a higher dimensional domain. So this is a very interesting issue. Now think of a large number of particles in a domain. Can you say something about the ergodicity of that system? And this is a story that's been going on for a long time, and now it reached a conclusion just last year by actually a Hungarian mathematician called Nándor Simányi, who proved the ergodicity of such systems. Which is actually, if you think about it, it's a large number of balls in a box, right? This is like a large number of molecules in this room. This is a gas, right? They run and collide, such things, okay? But they have a finite extension. And some other questions. So anyone who's interested in this topic and further details is welcome to ask questions or make comments or whatever. So thank you for your attention.